Hello everybody, welcome back to the Transformer Decoder part of the video. In this video, we will build the sublayers which are there inside the decoder layer, and then we'll continue building the entire transformer and train them as well. Let's start from where we left earlier. We had completed the encoder construction. Now we are going to the decoder part. The decoder, as you remember from our multi-head attention video or the first video where we introduced the transformer, decoder sentence will be input here either during the training part when we have the entire target sequences or the target sentence has been given. In this case we are doing a German to English translation, so the English input will be given here, the German sentences are given here, right, in this encoder part. So once the entire sequences has been given during the training part, positional encoding has happened, and then we will do the causal attention here. What is the causal attention? Where we apply a mask which prevent the model to look anything which is future words. In a sequence, we will be only giving whatever is the previous sequences from the current one and block all the others words which are coming after the current sentence. So that's the causal masking. We say this is a masked multi-head attention, or also we named it as causal attention. Then similar to the encoder block, we have the same thing which is repeating here. You can see the add norms are getting repeated here. After the add norm, this becomes your query, right? This becomes your query going into the cross attention layer, and the key value is coming from the attention. We discussed all of them, but just to repeat here. So the multi-head attention here is used twice. One is for the target sentence English getting converted into query, and another is the source sentence which is coming from the encoder as key and value. Then they are fed into the multi-head attention is the cross attention here. But the add norm layer, feed forward layer, again adding add norm layer is equivalent to the encoder. So this itself will create a block, this particular 2 number of multi-head attention in between add norm layer up to the feed forward, and then the final add norm is a block which will again get repeated n number of times, which is as per the paper 6 number, but this is a hyperparameter which you can adjust according to your task. Now once this block is done, which we will call it as the decoder layer, up to this last green border, starting from the multi-head attention. This is the center stuff, where I am putting my mouse, is a decoder layer. This decoder layer has to be repeated within decoder number of times, right? So let's go to the code and then build this part. Finally, you remember that the decoder layer will also have one more linear layer and the softmax. In our implementation, we will not implement this softmax. We'll just stop here in the linear projection after the add norm. That will be our decoder, and then instead of taking the output probabilities, we'll take the logits. You remember what is logit? Logit is just before the softmax conversion. Instead of converting the values as probability, if we take the values itself, that is called the logits just before the softmax layer. So we take the logits and then pass it to the accuracy loss function, who in turn will do the conversion using softmax to convert it as a probability and do the calculation. Fair enough. So let's go to the code now. Transformer decoder layer building. So what we are doing in the decoder layer, focus here. Basically we are again using the 2 number of multi-head, one for the causal attention, one is for the cross attention. That is why twice we are using, and the way it will be used is just by by setting up whether we want to pass the causal mask or not. That's how we can differentiate between these two. And in this particular code, I have not integrated fully the keras layer. So while my intention was to make them switch between these two, but finally I left it in between. You just focus that we are only using our own implementation. The keras layer implementation else block was completed in encoder, and the decoder I have not completed it. Okay, so that was about the initialization of the multi-head attention. Then we have the add norm, we know that there are 3 times the norm will be applied, so that's why norm 1, 2, 3 we have built as per the PPT. You will remember we have the feed forward network here, right? Then in the call you are taking the X value and the encoder output, because one will come from the target sentence, another will come from the source sentence. So this is your source sentence encoder output, and this is your target sentence. This is the positional embedded output, right? Then apply the MHA, multi-head attention 1, where the use causal must should be true. Go on, apply the add norm. Dropout is applied as per the original paper. To we'll be building several layers, 6 number of layers, and when you are building a deep neural network to prevent overfitting, you give a dropout, right? And it is only applied during training. Dropout is applied during training. During inference, no dropout. That's the switch here. Okay, going forward, you see this MHA2 has been applied, which is for the cross attention. Here, ideally, your causal mask should be false. I have made a mistake here. Use causal mask is equal to true is actually going here as well. This should be prevented, right? So it is left to you as exercise. You will see our final implementation, both in the custom implementation, what we have done with MHA, the multi-head attention, as well as the Keras implementation. We have done this mistake. I am not rectifying it because concept here is important. In your implementation, when you are following this code, you make this as false and then see what happens. Okay, fair enough. So this is where is the attention weight which is coming from the cross attention layer, and that's what is important for us. All these other blocks are not important. I mean, the weights we just not use it. Okay, then you are adding the add norm like the way we have said, right? And finally you are going to add the final add norm, passing it through the feed forward layer. You are giving the add norm, and that's why the layer stops, right? So norm 1, norm 2 and norm 3, all the 3 add norm has been added. What is that norm? Explained in the previous video. During encoder construction we have done it elaborately. What is the residual connection and what is the normalization, how they differ, the batch normalization and the layer normalization. All this we have discussed in our previous video. Now we are going to go to transformer decoder construction. Decoder is nothing but stacking up 6 number or n number of layers, encoder layers, and then finally adding one more linear projection, then give me the log it, right? That's what was the presentation. So same thing we are doing here. We have given number of layers and then running it within a loop to construct those many stack basically those many layers of decoder, but one is outside the loop just for the debugging purpose. Like in the encoder also we have done it. Ideally this also should have been inside it. Just to make the debug as true, I have done it. Okay, and then inside the call we take, this time we are taking the input without positional encoding, because within the decoder positional encoding will happen. So positional encoding, we collect the padding mask and then finally we just add this mask out here and then just give it here. Basically this is how you are calling the decoder layer, and then within a loop we are stacking up all those layers one by one, the stacking up the 6 number of layers up to the number of layers we were supposed to add them, right? So that's all about the transformer decoder block, matching exactly what we have displayed in the presentation. Now we are going to test it, right? Transformer decoder is initialized using our class, then pass 2 number of instances inside it. One is the just the sequences, right, which is the target sequence x2, and encoder out, which is the key value which is coming from the encoder, right? The key value which is coming from the source language. These are all output of the multi-head attention, which we have explained in the multi-head attention video. Basically how the splitting is happening, how before going to self attention we are again converting the first 2 dimension as a batch. Those we have explained. These are the different ways the mask has been applied. causal mask and the padding mask, combine them, and then finally the output should be, decoder output should be decoder sequence length, the batch decoder sequence length, and the D model dimension. Every output of the layer will match to the D model. That's how the attention is all designed, their main paper. So we have also made it as 512. While encoder was, if you recollect, 101 was the sequence, the output from the decoder will be matching the decoder sequence length. That is going to be the translated English sentence. Now we can move to the transformer model, which is basically joining them together. Here we are in the transformer model. You can see there is the encoder and there is a decoder. Both takes input as word converted as a sequence. Here also the same thing. The target language, which is English, converted as the sequence. Now coming to the Jupyter book, we are now showing that how we have built the transformer model. Very simple. We are initializing the encoder, we are initializing the decoder, and then finally we are passing it through the dense layer. That's what was there, right? So encoder takes the input, decoder takes the output, and the final attention weight is the weight which we can plot it for displaying the attention, and then finally it goes to the dense layer, which is the final layer, like we said, and instead of converting into softmax, instead of converting the output as probability, we are taking the values as is, which is called the logits. The layer just before the softmax is called the logits. So we pass this logit as the final output. Now let's come here and then see how we are going to train it. You have the transformer model. This is the transformer model that we are seeing here, and then you are passing two data. One is the source language, another is the target language. Two such instances we are passing as if two instances in a batch, and training is false at this moment because we are trying to do the inference, and it will give you all those debug output which we had seen. End of the day, this transformer is supposed to give you the transformer output will be two batch decoder output, which is the English sentence length, and the final output length, again a hyperparameter which we call it as DFF, the final output FF, feed forward networks final projection. So we are taking this as a vector which can be then finally converted as the probability of which word is there. To train this stuff, we need two things. One is a custom scheduler which we need to build. So you can see this is how the custom scheduler looks like. Okay, basically there is a warm-up step, and it takes about the dimension of the model using these two parameters depending on what is the number of step in a batch, how many examples are there, right? That's what is the step. So these are the step which is there, and then using those step you are trying to create a learning rate by using this formula, right? This is the formula using which you are doing it. But then this is exactly as per the original paper this formula was given. I have also done a custom schedule where you can give the parameter of the model warm up and the decay rate to adjust a little bit. When your number of example in a batch is not very large, then you can control the learning rate a little bit. I'm just going to show you how it looks like. For example, if you do my learning scheduler, I am showing you two. This time my step involved within the batch is around 3000. So I just adjusted it to give it a shape like this. Started with a very low number, then rapidly going up, then gradually decaying as the number of steps are proceeded, right? You see the original one with a 40,000 step will follow this pattern. So when it is not 40,000, we can expect with a lesser number of example in a batch, it will only increase, going up very rapidly. If your batch is within this range, it is gradually increasing. This decay will not come into picture. So if you're according to your number of steps in the batch, you can possibly readjust this value, right? But I have not done this. It is just for understanding. I have finally used this one where we can expect that it is actually increasing. The learning rate is increasing gradually. So that's about the learning rate implementation. Apart from that, you also have to build on custom accuracy. Here, this is where you have the accuracy function. Okay, all of this code I'm going to link it down below in the comment section. Even if I am not doing it immediately, follow my video. I'll be giving you this link there so that you can go through this code in the GitHub. But like I said, that I will encourage you to look at the screen, pause the video, and then type. That is how you will learn. Otherwise, looking at the code, it is not a kind of a storybook you just read and you understand. You have to practice it here, right? So basically, the accuracy function takes a real and the prediction value and then accordingly do it. Apart from that, what we are doing here, you are also applying the mask so that the accuracy is calculated correctly, right? This accuracy function and the loss function is, I have taken it from the TensorFlow original tutorial. So this code is also there. I have not made any changes except some comments and additional debug printing. Fair enough. So let me come back here. How now my model is basically little thinner model. So instead of 6 number of layers, I am using 2 number of layers. I have kept number of weights and 512 same, because in the paper they mentioned that when you divide 512 by a number or whatever, by the embedding by a number of heads, each head should have 64 as the dimension. That works well. So that's how I have kept this as the same. This 512, the last dimension which it is supposed to give you, output log it length, that is 2048 in the original paper, I guess. Here we are making it little smaller, which is 512. Dropout I have increased little bit from 0.1 to 0.2. And then finally I am fitting the data here, right? Fitting the data of with the trained data set. This data set has been converted. Our data, if you remember, are basically NumPy arrays of x1 and x2, source and target language, but I am converting them to a 10 shared data set through these lines, right? I am creating the data set as a 10 shared data set from this x1, x2 and the level. So the data set contains this source language, target language and the level. Level is shifted, if you remember all those. So all are there in our past videos. And that's what you have created a trained data set. You have also created a validation data set with 80% on training and 20% on the validation. Having done that, this is the same data which we pass through the training, our model, which is our fit model we have initialized somewhere. Here we are initializing our model which you have done, and then within the model use same optimizer and the learning schedule which you have created, right? And then finally fit the data. As you fit the data, because of the custom learning schedule, you will see that you have already crossed 50 epochs, but your accuracy function has not improved at all. Very slowly it is improving. It has started with very high negative value, going there gradually. I have taken a small set of data, but those data are very large. There are a lot of sequences there. Why I am doing so? Because I have this PC which is without GPU. I tried with larger data on Google, buying some GPU and doing all those, but eventually I see that this is demonstrating whatever we wanted to demonstrate. So I have done several training experimentation, and this training seems I can repeat this with a higher number of data on the Google. I am currently doing this training on my own PC without a GPU. I have built this PC, so there is a video there how we have built our own PC for this purpose, machine learning purpose, which is performing well even without GPU now. Now once it reaches accuracy 10, from that point onwards it starts improving. Okay, so I kept on doing the training because it's a small data, not taking too much of time. At the same time, we ensured that the validation accuracy is also correct, so we are not creating a huge gap between training and validation. And at the end we can see that it has reached around 71, let me see, yeah, around 68-71% of accuracy I could achieve through this, right? And the validation is also very close by, so it is not overfitting. Although you might be thinking that you have trained it such a high number of epoch, therefore it may be overfitting. So I have ensured that it is not overfitted. Then saved the weight and checked what is the parameter. We can see this is 32 million parameter, right? You can understand ChatGPT and others would be much higher. They are in the range of 170 billion and then gradually increasing. GPT-4 is 1.4 trillion or 1.3 trillion, 10 times the GPT 3.5. So why this parameter increases, you understand. For such a small model, we are already hitting this 32 million parameter, right? So transformer training is difficult and it's a large model. Okay. Now, whatever we have trained on that model, we just try to do a small testing where we have given a, this data, source data, only one of them, and this data, and just trying to match what is the predicted ID and the label ID with this. So we see that 189, 28, 41, 188, 28, 41. And last few couple of things we can see 17, 18, 291. There is some error here. Only the first few things have matched quite well. Prediction was that way closer at the beginning. At the end it has started losing, right? I mean, you need to improve the accuracy. We are only in the 68%. These are your attention weight. And finally, we have the attention plot function where you are giving only one sequence. This function will convert ID to token and token to ID. That is what it will do. And then plot function will just take the encoder input, use this as to convert the numbers to the actual word, and then finally plot the attention weight using the mat show. That's what is the main thing, right? Okay, come below. Here we are doing some plotting of how the attention has worked. Let's see that this is where you are taking, it is the example number 34. We are randomly picking up. So we see, yeah, this time even the 51159, 51159. So both the beginning and the ending has been predicted well for 34. If we look at the attention plot, we can see that this is coming out quite good at the beginning. In between it, attention was very poor, but again at the end it is doing very well. Basically word to word match. Between Germany and English, the length almost never matches. They are there is a wide variation. So the attention will be struggling at some places, or maybe it will have a vertical line like this where one word or many source word correspond to only one target word. That is why this vertical line will come. But more or less otherwise, it is following the diagonal pattern, which says that there is a word to word attention which it could detect. Similarly, we see some more, because of, like, say, unequal sequence length, and one word might be corresponding to multiple words, attention has done a little bit spread out. Also due to the fact that we have not trained adequately, we have only gone up to 70% accuracy. So if we improve, this will also improve. These are some of the attention plots which we are displaying. This has come very nicely. So this part completes our transformer building, including the attention plotting, right? Now we are going to go to the default implementation and then also show you, like we promised, that this will be also one more thing which we want to display to you. So when we tried with the default implementation of MHA is taken from here, you see the MHA is the default implementation. So when we did that, using this MHA, rest of the things are almost same. The encoder layer and the decoder layer, we have almost kept the same thing. Transformer finally using the encoder and decoder layer, and I have also made the similar mistake there where the MHA2 should have used the the decoder layer, where we should have used the causal mask false, MHA1 causal mask true, MHA2 causal mask should have been false. You try this out in your own implementation. Then what we see at the end is that this default implementation showed the similar pattern, that the learning, because of the low data set, we have taken a small data set. Accuracy function was improving very slowly in the beginning, but then it started improving. It went up to 97% as against 70%. After almost how much? 300 epochs, we have achieved 70%. Here it is much less. It is not that much. It is here, we can see this is around 20 epochs. Here it is 50, so 70, and here again 10. So around within 100 epochs, we were able to achieve 97% of accuracy. We took little bit more data here in this case that could have caused this one. Also, these are the EIN sum. You remember, our implementation was more focused on splitting module by module, and by this process we had to do several times shaping, reshaping, right? The masking was done manually. We had to understand that how to do it. We have inserted a highly negative number. When we go through the default implementation of MHA by the Keras layer, we observe there that they have done few improvement in terms of handling the numerical stability. Second is that they have implemented EIN sum. More effectively they are calculating the self attention. At the same time also they are doing the projection more effectively. So those are possibly the cases or the reason why this is showing more effective, more improvement with a similar set of data. In less number of epoch, it could achieve higher accuracy. Yeah, that completes the entire transformer tutorial. In the next video, we'll see that how this transformer can be used in different ways to address specific problems. Finally, leading up to GPT and our promise that we will go from RNN to the large language model. So how we'll go to the large language model, what is the large, how we are making it large is what will be step by step going. See you then, stay tuned. We have very exciting thing coming up in the next videos.